Hi viewers, in this video we will solve problem 8.31 from the book Heat Transfer J.P.Holman 10th edition. Here is a statement of the problem T1 from chapter 8. Two parallel planes 90 by 60 centimeters are separated by a distance of 60 centimeters. One plane is maintained at a temperatures of 800 Kelvin and has an emissivity of 0.6. The other plane is insulated. The planes are placed in a large room that is maintained at temperatures of 290 Kelvin. Calculate the temperatures of the insulated plane and the energy lost by the heated plane T1. The temperatures T1 of the heated plane, that is 800 Kelvin, and its emissivity E1, that is 0.6. Temperatures of the room, that is, let's say, T, and it is 290 Kelvin. So this is, let's say, plane 1, this is plane 2, this is its x dimension, this is its y dimension, and the distance between these two planes, that is d. So let's say the x value of one plane is 90 centimeter, y value, that is 60 centimeter. The distance between these two planes is d, and it is 60 centimeter. So to convert that into meters, just divide this centimeter value in by 100 and you will convert into meter. So you will get 0.9 meter, y, that is 0.6 meter, d, that is 0.6 meter. This is plane 1. It is at a higher temperature T1. This is plane second plane, that is at a temperature T2, and it is enclosed in a large room, and it is at a temperatures of T3 that is given. We need to find the heat transfer by this heated plate, that is Q1, that is our requirement to find, and the temperatures of the is cooled. Okay, before finding this heat lost by the heated plate and the temperatures of the this plane T2. So before make the solution to find this T1 and T2, the important thing that we need from this graph is to find the shape vectors f of 1, 2. So to find the f of 1, 2 from this graph, you need to find the x by d ratio and y by d ratio, and this x by y by d and x by d ratio coincide with each others, and you will get the corresponding shape vectors for this f of 1, 2. So first we will find the x by d ratio. What is x? That is 0.9 divided by 0.6, 1.5, and y by d ratio, that is 60 divided by 60, so you will get 1. So our point is 1.5. So now just move forward and see whether it coincides with y by d ratio curve, and this is 1, so here we get the point. Now from this, move at this left side such that it's coincide with this y-axis, so here you will get the shape vector for this two planes f of 1, 2, and this is almost 0 point. So the shape vector f of 1, 2 from this graph with the help of this ratio is 0.25. Now from the enclosure theorem, f of 1, 1 plus f of 1, 2 plus f of 1, 3 is equal to 1. So for this plane f of 1, 1, the shape vector is 0, because for flat surface f of 1, 1 is 0, and for f of 1 2 it is 0.25 plus f of 1 3 that is equal to 1. So you will get the f of 1 3 value 1 minus 0. Area A1 is equal to area A2, and that is 0.6 multiplies 0.9, and you will get its area of the both planes, that is 0.54. So by reciprocity theorems, if I say area A1 f of 1 3 is equal to area 2 f of 2 3, these two are will be same. If area is the same, it will cancel out. So I can say that f of 1 3 shape factor is equal to f of 2 3 shape factors, and that is 0.75. So all the shape factor, that is all requirement in order to solve this problem, has been determined. So we didn't require this graph. So I will remove this from the display, so we'll get the maximum workspace. Okay, now I am writing the resistance network diagram for this problem 831. So this is, let's say, emissivity of the heated plane, then its surface resistance, then its radiosity J1, then space resistance, then heat loss to the J3 room, and J3 is equal to EB because it is very large in volume in area, so its surface resistance is considered to be 0. Insulated plate, that is J2, and it is equal to EB2, its emissive power, because its surface resistance is 0. As it is mentioned, it is insulated. So when there is a heat transfer, plane surface 1 and 2, there must be space resistance between them. Similarly, space resistance between the room and the plane 2, when there is a heat transfer of E1 divided by area A1 E1, then space resistance between J1 and J3, that is equal to 1 divided by A1 f of 1 3. Then this is again space resistance between J1 and J2, and it is 1 over A1 f of 1 2. This is 1 over area 2. So this is resistance 1, this is resistance 2, this is resistance 3, and this is resistance 4, that is offered to the heat lost by the heated plate. Resistance 1 is equal to 1 over minus emissivity 1 divided by area 1 emissivity 1, and 1 minus emissivity 1, that is 0.6 divided by area, that is 0.54 multiplied by 0.6. We will get its value, that is 1.2345. All the resistance that is in the, you can see in this resistance network diagram, has been determined its value. All things are very easy. Now for we need to find the net resistance, the total resistance that you see in this resistance network diagram, that is offered to the heat loss by the heat gain. So first just focus on the resistance that is in the triangle. So first we will find its net resistance, and that net resistance, equivalent resistance, are in series with its R1, so we will simply add with it. So just focus on these resistance. So you can see that So you can see that the resistance R4 and R3 are in series, so we will simply add with each other, and let's say its equivalent resistance is R5, and that is equal to R4 plus R3. So what is R4 value? That is 7.409 plus R3, that is 2.469. Just add with each other, so you will get the R5, and that is equivalent resistance of these two, R4 and R3, and you will get its value, that is 9.876. Now this resistance R5, that is the equivalent of these two resistance. If you see, it is in parallel with R2, so the equivalent and the net resistance of R5 and R2 is, let's say, R6, so it will be 1 over R6, and that is 1 over R5 plus 1 over R2, so that are in parallel. That's why I write in such form. So the final R6 value after simplifications you will get, that is R2. Also, this resistance R6 is the net resistance of this triangular shape resistance. So it is the net resistance of R2, R3, R4. So this is R6. So in terms of this resistance that are in triangular shape, I can write the R6, and it is in series with R1. So the total resistance of this resistance network diagram is simply equal to RT, that is R total, R1 plus R6. So what is R1? That is 1.2345 plus R6, that is 1.9752. So R total, you will get its value, that is 3.2097. The heat transfer from this heated pan is equal to Q1 is AB1 minus AB3 divided by its total resistance that was offered to its heat lost. What is AB1? So the value of AB1 is equal to sigma P1 to the power 4, that is 5.67 multiplied 10 to the power minus 8 multiplied by T1, and T1 is given in the statement 800 to the power 4. So after simplification on calculator, you will get its value. Just put in these formulas. Total resistance has been calculated, EB1 and EB3, to find the Q1. And this is the first answer of this statement. Next is to find the temperatures of the second plane. Or to find the temperatures of this plane T2, look at the node analysis at this J2. So the J1 minus J2 divided by its space resistance plus J3 minus J2 divided by its space resistance will be equal to 0. This is the summation of all the heat entering to this node 2 will be 0. Next we need to find the temperature T2. This is the temperatures of the second plane. So to find that temperature of the second plane, we need to find find the value of J2 radiosity with the help of this resistance network diagram. So all the heat current entering to the node J2 summations will be 0. So the heat current that is entering from J1 to J2, that is equal to J2 J1 minus J2 divided by its space resistance, that is R4, and its value is here, that is R4. The heat current that is entering from radiosity or from the room AB3, that is AB3 minus J2 divided by its space resistance, that is R3. Here its value must be equal to 0. Okay, now put the values in these equations. Here J1 value is determined, B3 value is determined already, R4 and R3 value you can see from here. So I'm entering its value now. Now simplify these equations to find the value of J2. I'm simplifying it. Multiply each terms of this equation with the product of these two denominator. Multiply this value with each others and this value with each others, and add the coefficient of J2 with each other and write the sign in negative. So the final simplified versions of these equations you will get 38,625 minus 9.876 J2. So shift this terms to the right side of the equation and then divide this value with coefficient of the J2. So you will get the value of J2, that is equal to 38,625 divided by 9.876. So after divisions you will get the J. It is 3911 watt per meter square. Next is to find the temperatures of the planes 2. So EB2 is equal to J2 and it is equal to sigma E2 to the power 4. So just enter the values and I'm writing equation for T2. So T2 will be equal to J2 divided by sigma and under the fourth root. So just enter the value and take fourth roots of it after division with sigma. So J2, that is 3911 divided by 5.67, multiply it into the power minus 8. Solve this on calculator and you will get the temperatures of the second 22, that is almost 512.5 Kelvin. And this is the final answers of this statement. I hope you understand. If you still have any confusion, you can ask. Please subscribe my channel if you haven't subscribed yet. Thank you.